All right, so dilations. Now, I've got to say, I was really kind of sad that Mrs. Holbert got to teach you guys dilations and not me, because I think in my real life, the two things that we learn in this class that I personally, in my own personal real life, not like my life as a math teacher, my life as like a normal human being, the two things that I do the most are rates, figuring out distances and times. How long is it going to take us to drive to grandma's house if we drive this fast? How long it takes us if we drive this fast? And that sort of a thing. And dilations. Honestly, I'm a quilter and I do what's called paper piecing. And when you paper piece, you've got a piece of paper that you're literally sewing on. And I'm never happy with the size they give me. Sometimes I want to make it smaller. Sometimes I want to make it bigger. Usually I want to make it smaller. And so I have to make photocopies of these things, and I have to figure out the scale that I need to tell my printer, hey, photocopy this at 45% or at 60% or at 150%. I did 150% one the other day because it was an 8-inch and I needed to go to a 12-inch. And anyway, I do those really quite frequently. So let's review how to do dilations. Basically, dilations is you got your phone screen, you go womp womp womp. That's what we're doing with dilations. We're making these shapes bigger and smaller. A prime equals R times A, where R is the factor of dilation, right? So we're going to figure out what the factor is on this one. We have the center of dilation and we are dilating. We're going to do it both ways because you can go bigger and you can also go smaller. So let's say we're going from ABC to DEF. What is the factor of dilation there? So we've got two triangles and we can really just use one set of sides to figure out which one we want to use. So we're going to use this side. We're going to use 6 and 12. Those are the corresponding sides, the ones that we're going to be using. We know that these triangles are similar because all three angles are equal. We can also test if they're similar if two of their sides are proportional, okay? So I know that A prime equals R times A, and I'm trying to figure out the R that gets me from triangle ABC to triangle DEF. So DE would be what AB prime would be, so that's 12. 12 equals R times, over here, that same corresponding side is 6. So I've got R times 6. I want to get the R alone. The opposite of multiplication is division, so I'm going to divide both sides by 6. And this R equals 2. So I had a scale factor of 2 when we went from this triangle to this triangle. Now, what if we want to go from this triangle to that triangle? So I would say that now this is the prime. We have DE prime is 6. So 6 equals R times, now that we're starting with 12, right? R times 12, still multiplied. So we get rid of if we have a number by our variable that's multiplied, the opposite of multiplication is division. So we're going to divide both sides by 12. 6 over 12 is 1 over 2, and we have R equals 1/2. Now, if you look at this, you will see to go from one to the other, it's the reciprocal. So to go from the small one to the big one, we do it by a factor of 2. To go from the big one to the small one, it's 1/2. So like if I had two triangles, and to get from the small one to the big one, R would equal 5, let's say. To get from the big one back to the small one, R would equal 1 over 5, which is really, really nice. And I used that the other day when I went from my 8 to my 12, I had an 8-inch quilt block and I needed it to be 12 inches and I needed to make the copy of this thing. So 8 to 12, right? I needed to go bigger. So I know that 12 equals R times 8. What? I can do this. R times 8, the opposite of multiplication is division, so I'm going to divide. 12 divided by 8 is 1.5, 1.5. So I had to, on my copier, I had to say, hey, we need to go to 150%. I had to turn it into a percentage, 150% on my copier to make it bigger. Now, one time I went from a 12-inch quilt block to, because I'm a special kind of special, I went from a 12-inch quilt block to literally a 1.5-inch quilt block. And the reason why I'm joking that I'm a special kind of special is because sewing that, those seams were so tiny. Oh my gosh, it was so hard to sew. But totally I did it. I actually really like that kind of a challenge. So I had to tell my copier to go down way teeny tiny small. And I actually had to do it in 2 steps. I had that math problem all planned out. And I didn't get to use it, and I was so sad. So here we have 2 triangles, and we need to figure out what x is. Now, first thing we need to figure out is, are these similar triangles? So in order to be similar triangles, they need to have 2 angles that are the same, because if they have 2 angles that are the same, then automatically the third angle is the same, or we need to know that 2 of the sides are proportional. Well, we don't know that 2 of the sides are proportional, but we do know that they share this angle right there. So that angle has to be congruent. It's congruent with itself. Like, it's hard to not be congruent with yourself, right? Like, I am my own twin. And then this is the right angle, and this is the right angle. So we have 2 angles. Boom, we have similar triangles. Okay. So what is x going to be? So we have 12 here, and we have 24 here. So I need this total length, though, which is 12 plus 24, which is 36. Okay. So so I need so these are going to be proportional. Okay. So let's figure out what a constant of proportionality is. So I know that r prime equals, no, I'm going to call it a prime. A prime equals r times a, right? But in this case, a prime is 36. We've got this whole long triangle. This triangle is dilated out to this one. Wah, long, long. Equals r times a, which is 12, is this side. You know, I'm just using arbitrary letters here. So take this side, dilate it out to get this triangle, and we get this. So I'm going to divide by 12. I'm going to divide by 12, and so we get r equals 3. So now if I want to find this side, or if I want to find this side, I'm going to use this side. So AB is going to equal r times EC, right? Which equals 1.8. EC is 1.8 times r, which is 3. Which equals, I'm going to actually pop out my calculator on that one, 1.8 times 3. Oh, wait, not 18. Nope. Clear. 1.8 times 3 equals 5.4. So this x is 5.4 millimeters long. Okay. So here I am going to show you, I'm actually going to pop over, I popped out of sharing the screen. I'm going to hop on over to my Google Docs where we actually have this. Well, I can do it over here. I was going to maybe do it on my, on the, oh gosh, I'm all over the place. I apologize. Keep popping out of where I want to be. So let's just open up Cami Apps again because it's not working to open the Google Docs as easily as I want. So let's do the dilations again. Let's open it up again. We can do it either way. We'll go ahead and do it this way. I was going to do it kind of a creative way. But when you're on a coordinate plane, dilations on a coordinate plane are really, really cool because if you are dilating from the origin, you just have to look at the coordinates and multiply by the coordinates. So let's say we're going to dilate from the origin by a scale factor of r equals 3. Okay. So this is the point. We have the points 1, 1 on our little notched out square here. We have the point. This is the point. So this is a point 1, 1, and it is in purple. Okay. In red, we have the point 3, 1. Okay, 3, 1. In green, we have the point 3, 2. In orange, we are going to have the point 2, 2. In, let's get another color, purple. No, we already have purple. In black, we're going to have the point 2, 3. And then one more color. We're going to have, do we have green yet? Pink. We have pink. We're going to have the point 1, 3. Okay. So to find the points of this new thing, doing this on the coordinate plane is really, really slick because you're just going to multiply the values of each of these coordinates by this dilation factor. So instead of 1, 1, it'll be 1 times 3, which is 3. And then 1 times 3, which is still 3. Didn't change. So I'm going to do 3, 3, and there is that point. Boom, right there. That's the purple one. Okay, let's do the red one next. So we are going to, okay, we have the point 3, 1. So multiply 3 times 3, which is 9. 1 times 3 is still 3. Has not changed. So we have the point 9, 3. And we can drop a point right there. So 9, 1, 2, 3. Boom. Okay. So now let's do the green one. The green one is right here. It's 3, 2. So we're going to multiply both of those numbers by 3. 3 times 3 is 9. 2 times 3 is 6. And we have the point 9, 6 is going to be our green one. 9, 6. And that is up there, right there. Okay. And then for orange, we have the point 2, 2. Well, 2 times 3 is 6, and 2 times 3 is also 6. So we have the point 6, 6. And let me drop a point right there, 6 and 6, and boom. Okay. 2, 3, this one's going to be in black. So we have the point 2 times 3 is still 6. 3 times 3 is 9. I'm glad I can multiply by 3. Okay, so we have the point 6, 9, and then boom, right there. And then the last point, and then we will connect our dots, is the pink one. And it is 1, 3. 1 times 3 is still 3, and 3 times 3 is 9. So we have this pink point at 3, 9. And if you look, it's the exact same shape we had before, but it's 3 times as big. And it's so slick and easy to do it on the coordinate plane. I love doing it on the coordinate plane. It's really quite easy. I'm going to connect the dots. Oh, I don't actually want them to be pink, though. We're going to make them black. So we're going to connect these dots just like that. Oh, the bell rang and it startled me. Did you guys know that I'm a little jumpy sometimes? Okay, so check that out. So if you have to dilate on a coordinate plane, it is actually really, really slick and easy to do so. And then if you want to look all 3D about it, you can, oh wait, we're dilated from the origin. That's right. So we need to have these extend to the origin. So you can have it head to the origin, but only go that far, right? Because it's dilated from the origin. Oops, I didn't quite go out far enough. Anyway, I'm just showing you how to make a cool 3D perspective, but then it only goes that far. Then the orange one, and the green one. Anyway, it looks all cool in 3D like, right? Anyway, so there's that for you. So that's dilations. I enjoy dilations. Oh, here's another similar triangles. We do another similar triangles. I totally forgot about that one, and I got off on my thing there. Similar triangles. So are these similar? They have a angle in common, and they have another angle in common. So they're similar. We know that So if you rotate this one down, then they match up. So the 10 actually matches up with the 5. And this 3, its corresponding side is the U, not the LK one. So let's figure out what the factor dilation is. So I know that if I want to go from this small one to this big one, that 10 equals R times 5. Divide both sides by 5 to get that R alone, and R equals 2. So then to find out what this U is, and I kind of look like I'm crossing it out there, to make it to figure out what this U is, I have this side. U is going to be R times 3, which is 2 times 3, which is 6. So that one's pretty straightforward, 6 meters. But they work no matter what. Anyway, let me know if you have any questions or any problems on any of these. I'm happy to help. Bye.